of MSE equals to sigma square plus something else, where the second term is the constant and always greater than or equals to 0. If this term is small enough, it means that we have evidence that on of tau I equals to 0, so we won't reach as 0. And if this term is very large, it means that we have stronger evidence that there's some tau I different to 0. It means that we reach as 0. Equivalent to say that we will have stronger confidence to reach as 0 in case that MSB must be larger than MSE, right? Because MSE only equals to sigma square, but here is equals to sigma square plus something else, and the constant term here depending on tau I. So if tau I different to 0, so sigma square plus some positive value, so of course MSB much greater than MSE, right? So that's the reason why we consider the fraction between MSB over MSE. Okay, as I have shown that we have stronger evidence to reach as 0 if MSB greater than MSB as large as possible. So it means that this fraction we want is as large as possible. Okay, as large as possible, it means that we want this constant must be greater than some positive value. If C is very large, we have stronger confidence to reach as 0. If C is very small, so we have lower confidence to reach as 0. So C will be the critical value. That's the constant we want to find. Okay. And according to the definition, the probability of reaching as 0 always equals to the significant level alpha. Okay. Now, always remember that working with probability, we need to know distributions. Okay. Distribution of this fraction MSB over MSE. If we don't know its distribution, if we don't know distribution of the random variable, of course we can't calculate the probability. So it's return to question about the distribution of MSB over MSE. Okay, and here one small time, we accept the theorem that let's consider the fraction f equals to MSB over MSE. Okay. MSB over MSE. And under the assumption that S0 is true, then F follow Fisher distribution with degrees of freedom df1 and df2. Okay. The Fisher distributions will be the distribution always positive. Okay, the Fisher distributions always positive. This is very clearly that MSB and MSE always positive. So Fisher distribution also always positive. It depends on 2 degrees of freedom. df1 is degree of freedom on the numerator. Degree of freedom. Okay, and in this case, degree of freedom of MSB is just the denominator. On the way we calculate MSB, we have k minus 1. df2 is the denominator, degree of freedom. In this case, we have k n minus 1. Okay. And the Fisher distribution, remember that it's always positive. Okay. So, return to our equation. We need the probability of f greater than c equals to alpha, where c is the constant, the critical value that we want to find. Okay. So, as we usually do, the probability, we need the probability of f greater than c equals to alpha. The probability means the area. Means that we want the area under the density function and greater than the constancy exactly equals to alpha. So, can you recognize the position such that the area under the curve of the density function and greater than this value exactly equals to alpha will be the upper quantile. Okay, this is the upper quantile of f at alpha, of course corresponding to the f1 and the f2. And of course, got the upper quantile of the Fisher distributions. We use the table of Fisher distributions. This is the constant. Okay, so we have that. So it means that we already done. The statistic value will be MSB over MSE. Okay, and the rejected regions, we should reject as 0 in case that f greater than c, where c is the upper quantile corresponding to the probability alpha, the f1 and the f2 of the Fisher distributions. We have done the test, the hypothesis test. Okay, return to the slides. Okay, here on this slide, I summarize the Anova corresponding to the f-test. This is the f-test because we use Fisher distribution. The test statistic value is f0 equals to MSB over MSE. 0 is mean that under the assumption that f0 is true. Okay, then f0 has the Fisher distributions with k-1 and k-1 degrees of freedom. Given significant level alpha, we should reject f0 if the test statistic value greater than the theoretical value, which is the upper quantile corresponding to alpha. Okay, as I already drew on the board. Okay, that's we have done. Here, this is cross the table, the Anova table. It just means that we summarize the calculation into the table. You can see that the first row we indicate, the first column we indicate the source of variation. We know that we have the total variability is decomposing into the variability due to treatment. It means the effect of X on Y. The variability due to the error term. It means that all of the things that onto affect Y, but we ignore and we call this the random error. Okay. So for each source of variability, we calculate the sum, the total sum. We given degree of freedom. Take the sum over degree of freedom. We have the mean. We have the mean variability. And F equals to the fraction between MSB over MSE. That's all. This is the Anova table. It's just the summary of the Anova calculations. That's all. Okay. Now practice. Using the Anova model, we have done together. Return to example 1 and we try to answer for the question whether we should reject R0 or not. Okay. Now we return to our question whether the Howard concentration really affect the tensile strength or not. Suppose that the Anova assumption already hold. Okay. I left you a few minutes. You try to do it by yourself, step by step. Then we do it together. Okay. 5 more minutes for you. Okay, so we can done this exercise very quickly. Actually, the Anova method is very useful in data analysis. But for doing the exercise, in my opinion, it's not difficult. Okay, return to the broth. And please ready with your calculator, because I need your calculation. Now, scroll down. Always, first step, write down the hypothesis. This is example 1. We have S0 is the 1 equals to, okay, we have K equals to 4 because we have 4 levels. N equals to 6. So totally we have N equals to K multiply N. So we have 24 observations. Okay. We have third 1 equals to third 2 equals to third 3 equals to third 4 and equals to 0. Okay, it means that S0 means we need both of notations, and the meaning means that the Harwood concentrations doesn't affect the tensile strength. H1 is there exists one I such that I from 1 to 4 and tau I different to 0. If tau I different to 0 means it means that the Harwood concentration affect the tensile strength. Okay. So we have done step 1, stating the hypothesis S0 and S1. Second step, to get the test statistic S0, we need MSB over MSE. So to have MSB, we need HSB and SSE. Okay. So firstly, I need to calculate HSD. Okay. To calculate HSD, we have the formula. Let's return to the formula for you. Scroll down to the formula of HSD, SSB, and SSB. Okay, see here. We have HSD, we have 2 formulas. It's just the sum of each observation minus the total average and test square, the sum square. Or using the computational formula, I usually use the second one. It's just the sum square minus the total sum. You take the square over the total number of observations. Okay, so return to our table. Luckily, in this table, you already given the total sum. You already given the total sum. You already given the sum of each treatment. But remember that usually you're not given the last 2 columns. You need to calculate it by yourself. Okay. Now, So now we need the sum square. Maybe look at your slides. We need, please use your calculator and give me some of the sum. Why I say square? It means that we need the sum square of each observation here. Okay, we have totally 20 observations. So please use your calculator and tell me the sum square of I. Okay, what is the sum square of observations? Please use your calculator and give me the value. Calculate the sum square, why I say here. Have you done? I need the sum square, why I say. Who has done? I'm waiting for your answer. I need the sum squares to continue.